Hello everyone, we are continuing our video series on acid-base equilibria with buffers. So a buffer solution is going to be something that contains an appreciable amount of a weak conjugate acid-base pair. And the purpose of buffer solutions is to resist a change in pH when we add a small amount of either a strong acid or a strong base. And this is extremely important in biological systems. So our stomachs are considered very acidic, our blood is slightly basic, and we need to keep those within a very set pH range. Okay, so whenever something disturbs the system, if you add either a strong acid or a strong base to it, we have to have something called a buffer to resist that change in pH so that the biological system can live. Okay, so buffers are very important. We have two examples here. You've got the acetic acid, CH3COOH, and its conjugate weak base. And so remember, when you've got that salt, you can remove the inert ion. And then if sodium has a positive charge, then that means that your acetate ion will have a negative charge. And another example, of course, is ammonia and ammonium. And so that salt, the ammonium salt, we can remove that inert anion and give that ammonium its positive charge. And we have a little picture down here where you can see you've got two solutions starting out on the left. Both are yellow, and what's causing it to be yellow is a pH indicator. And so that pH indicator is yellow when the pH is at 8. And so you have an unbuffered and a buffered solution. Well, if we add a strong acid to both of those solutions, you can see a color change in the unbuffered where it becomes very acidic when we add that strong acid, but the buffer remains the same at about a pH of 8. Okay, so that's the importance of a buffer, is to resist a change in the pH. So let's look at a few examples and determine if those are buffer systems. And so remember, by definition, a buffer system needs to be a conjugate acid pair, and both have to be weak. So whenever I'm looking at a pair of compounds and I'm trying to determine, the first thing I want to look for is, do I see a strong acid? Okay, because if I see a strong acid, then that already eliminates that as a possibility, because they have to be weak acid, weak base. A weak acid, weak base pair. So the first salt, we'll have to break apart the salts into their ions to see what we've got. So KF, potassium fluoride, will break apart into a potassium ion and a fluoride ion. And then the second one, we've got potassium carbonate, K2CO3, will break apart into 2 potassium ions plus a carbonate ion. Okay. Of course, we know the potassiums are inert. Those aren't going to do anything. And so we're left with this F negative, the fluoride ion, and the carbonate ion. Carbonate is considered a weak base. The fluoride ion is negligible, right? It is also a weak base because hydrofluoric acid is a weak acid. But the problem is that this is not a conjugate weak acid, weak base pair, right? Neither one of those have a hydrogen, first off, and second off, you don't have the ions that are the same. So that cannot be a buffer. And that's because this is not a conjugate pair. And my first instinct, the reason that I realized it wasn't a conjugate pair, was no hydrogens. Okay. Beyond that, even if you have hydrogens, the ions need to match up, and they do not. Looking at the second example, again, let's first start by asking, are there any strong acids? So strong acids present? No, neither one of these, right? HCN is not one of the strong acids that we have memorized. Okay, so if neither are a strong acid, then the next thing we're going to do is break the salts. Okay, and the first example, HCN, that's not a salt. We know it's not a strong acid. It does have a hydrogen present, and so that must be a weak acid. Okay, but the second one, sodium cyanide, we can break apart into its ions, where we get Na plus and Cn negative. Okay, the sodium ion is inert, so we can ignore that. And then we've got this Cn negative. And the question is that the conjugate base of HCN? And yes, it is, right? If we remove a hydrogen from HCN, we're left with that cyanide ion, Cn negative. And so, yes, this is a conjugate acid-base pair. So we've got HCN and Cn negative. And so, yes, this is a buffer. Okay, so I am checking to see if I have a strong acid. If I do, it automatically eliminates that it cannot be a buffer system. If there's no strong acids, then I see if I've got a weak acid, and then I break apart any salts to see if I've got the conjugate weak base. Okay, next set of examples. First question I always ask, is there a strong acid? And yes, HNO3 is one of the 6 strong acids that we have memorized, and so no buffer here, right? As soon as we find that there is there's a strong acid, it eliminates the possibility of having a buffer. Okay, and then the last example, not a strong acid, H3PO3, phosphorus acid is considered a weak acid. Okay, and so then I'm going to break apart my salt, the LiH2PO3. I think we can see where this is going. The lithium ion will be inert, and then we have the H2PO3. Oh, oops, H2PO3 negative, and of course that is the conjugate base, right, to removing a hydrogen from H3PO3 from phosphorus acid. And so yes, this is a buffer. Okay, so how do the buffers work? In a strong acid, if we add a strong acid to pure water, we've seen how it fully disassociates into that hydronium ion, right? So if I have a 3 molar of hydrochloric acid, you're going to have 3 molar of the hydronium ion in pure water. Now, in a buffer solution, if I add that same 3 molar hydrochloric acid, that hydronium ion is then going to react with the weak conjugate base that's in the buffer solution. Okay, and when it does that, it's basically going to form more of that weak acid, and it's going to reestablish equilibrium. Okay, and we've got an image here where if I add the hydronium ion, so we're starting out with a buffer solution that's equal parts of the conjugate acid-base pair, and I add that hydronium ion, it's going to push the equilibrium towards the reactant side to form a larger amount of that weak acid, and it will reduce the amount of the conjugate base, but we still have both present. And so if we were to calculate the pH of this solution, we'll see a slight change, but it won't be as drastic as just having pure hydronium ions in solution, right? So that's kind of how the buffer solution works, is that when we add the strong acid, it will react with the conjugate base, or if we add a strong base, it would react with the conjugate acid. And so we see if we add the hydroxide ion, it's going to react with that weak acid and form more of your conjugate base here. So let's try an example where we calculate the pH of a buffer solution. Okay. So remember, when we are calculating the pH, the whole purpose is that we need to find that hydronium ion concentration at equilibrium. Okay, and so at some point we're probably going to need an ice table. And so you're going to find this is very similar to, again, when we did the ice tables for the weak acids. We just have one extra little catch here. And that extra catch is that we are starting out with some amount of the weak base as well. So let's go ahead and generalize this equation. I think it might be helpful, where we have the phosphoric acid. Okay, so let's mark that out and write it as HA, just our general acid notation. And then, of course, the other amount that they give us, that 0.25 of the KH2PO4, we can remove that inert cation, and that leaves us with the conjugate base. And so we can mark that out as well and rewrite it as a negative. Okay, and then the Ka value that they give us, that is for the conjugate acid. Okay, so just kind of eliminates or shorthands the acid and the base. So the next step is that when we're forming those ice tables, we need the concentrations. And they don't give us the concentrations, but they give us the moles of each and the volume in liters. So let's go ahead and calculate the concentration of the weak acid and the weak base. So starting out, our concentration of weak acid is 0.155 moles divided by the volume of 0.5 liters. Okay, so we get the starting concentration of the acid is 0.31 molarity. Do the same thing for the base. Okay, the base, we've got 0.25 moles. Divided by the 0.5 liters. And that will give us a concentration of 0.500 molarity. Okay, we can see that that Ka value would be larger than the Kb value if we were to calculate it, right? 10 to the negative third is getting closer to a value of 1. And so let's write that acid first. We also know that both of these are technically considered acidic in water. So we've got H3PO4, which is an acid, and H2PO4 negative is also considered a weak acid in water. So we know that the hydronium ion is going to be produced. So let me make a note of that. And what I'm doing is I'm explaining why are we using the general reaction for the acid rather than the general reaction for the base. And we're choosing to use the general reaction of the acid because both are considered acidic, the acid and its conjugate weak base. And this is compared to water. Okay, so we know that the hydronium ion is going to be produced compared to the hydroxide ion, and so we want to use that general reaction where we have the HA, and we'll put the water over the arrow since we don't need it in the ice chart, and H3O plus A negative. Okay, we have the initial amounts, and this time it's not 0 and 0 on the product side, right? We have that original concentration of the weak acid, that's the 0.310 molar, and then we also have a starting amount of that weak base, and that's going to be 0.5. Now we still don't have any any hydronium ion, so that will be 0. And of course, the acid is going to be where we subtract, so minus X. We're going to form some amount of hydronium ion, and that's why we have to have 0 plus x on the product side, minus x on the reactant side. And we are going to assume that 5% rule again, but this time we're going to assume it twice. Right, we're going to assume that the minus x is insignificant, and we're also going to assume that the plus x is insignificant as well. And so the Ka value will be equal to the products, and now the two products, it's not x and x, we have x and we have the 0.5. Divided by the original concentration of the acid, which is the 0.3. Okay, and we know the value of Ka. They give it to us. That's that 7.5 times 10 to the negative third. Okay, and we'll go ahead and manipulate the equation where we multiply by the 0.310 and divide by the 0.5. And that will give us x. And let's not forget what x is, right? The whole point of determining what x is that that is the hydronium ion concentration at equilibrium that we're looking for in order to determine that pH. And so x, and let's see if I've got another sheet. So when we solve for x, we get 0.00465, remembering that that is the hydronium ion concentration. And just to double check and remind ourselves to assume that 5% rule, the x value needed to be significantly less than the 0.31 as well as the 0.5. And so all we have to do is compare it to the 0.31, and you will find that that is much less, it's less than the 5% of 0.31. Okay, so that's just saying yes, the 5% rule does work. Okay, but what we care about is that value of x, looking for that pH. Remember, pH will be equal to the negative log of that value of x. And of course, x has two significant figures because that Ka value had two significant figures. And so we want to have two decimal places out for the pH, and we get 2.33. Okay, we'll go ahead and stop here, and then in the next video we'll pick up with the buffer solutions, but we'll look at the Henderson-Hasselbalch equation as well as buffer capacity, and then we'll work on some problems where we add either a strong acid or a strong base to that buffer solution.